Okay, folks, so we're going to move on to Chapter 3 homework, where we look at problems 1, 2, 5, 11, 15, and 16. This chapter will have a lot less math than the last chapter, so hopefully it'll be a lot smoother to go through. Now, they're not all going to be so nice and lacking on math, but a majority of them don't have to have a lot of math. We're going to try to do a lot more theoretical work where we can, some thinking questions where we can. But okay, let's go ahead and go to the doc cam and look at this. So problem 1. Problem 1 has us looking at the Lewis structures of oxygen and ozone, and looking at the reactions of oxygen cleaving to form two oxygens, which we kind of looked at last chapter. That has an enthalpy of positive 498, but O plus O2 going to ozone only has an enthalpy of 105. Now, hypothetically, half of 498 is what, like 274, something like that. Half of this is 249. It's 249.17. So half of an oxygen, you might expect, oh, that should be 249, but it's 105. And so that's where we want to kind of look at this and use this to kind of think about our bond orders. The first step is to draw a proper Lewis structure for this. Proper Lewis structure, if you're trying to draw a Lewis structure for oxygen, you have O, you put 1, 2, 3, 4, and then we 1, 2, 3, 4, and you put a double bond, and look, oh, hey, that a bond order of 2. Bond order of 2. So I'm predicting that energy. If we're drawing ozone, with O, we have O, we end up having a 1, 2, 3, 4, 6. You have 1, 2. I'm going to draw, and then we end up having like that with a resonance structure, that this ends up having a positive and this ends up having a negative, and you resonate between the two. So resonance structure kind of is a stabilization effect that essentially has you would expect a bond order of 1 with but a resonance structure actually has a bond order of 1/2. So with that in mind, you say, okay, if you look at the bond enthalpy of a double bond, bond enthalpy of an OO double bond is 497. The bond enthalpy of a single bond, of a OO single bond, is 146. Yet we don't quite see 146 or 490. We see 497 essentially there, which matches up pretty close to enthalpy we get from the tables. So this one matches up reasonably well to what you would expect. But this one doesn't match up pretty well. It's 39 kilojoules off. What this means, it's not just a single bond that we're adding a partial bond essentially. You would expect the enthalpy of formation to be something like, okay, you'd have a 497 minus 2x's to give us negative 105. What you would expect, well, x to be 301. And the average of 301, if we split that in half, is something like 150 essentially. But if we average out 146 and 497, if we average up 146 and 497, we add up our 146 with our single bond and our 497 with our double bond, and we divide that by 2, we get a average bond enthalpy of 321.5. So how do we get the products minus the reactants to give us this energy? And that has to do with the fact that the bond order is not 1 or 2 in ozone, but it's bond order somewhere between the two, which is a bond order of 1.5 with a bond enthalpy of about 321. And so 321 pretty much matches up the expected 301 you might see. But basically, ozone is a partial bond order between bond order of 1 and 2, which means its bond length is longer / weaker than a double bond, but stronger and shorter than a single bond. So that's going to tell us something about its properties. But that's why it has the energy it has. It's because it's not quite a single bond, not quite a double bond, even though the Lewis structure shows it drawn as a single bond. I kind of skipped a little steps, but so the enthalpy of ozone is 497. Well, the enthalpy of a double bond, 497. Okay, so now, okay. Let me say now number 2. Number 2 is like looking at the feedback mechanism. It's been suggested that the loss of ozone in the stratosphere could lead to a negative feedback that might allow more ozone to be produced. Explain why the feedback is possible. This self-healing does in fact occur, but only to a small effect. So this is without any catalyst. We're looking at the 4 reactions we have. We can have O2 plus light goes to 2O. We can have O plus ozone goes to 2O2. We can have ozone plus light forms O and O2. And we can have O2 plus O goes to ozone. Those 4 equations. 4 equations are the ones we want to consider. No more. No more. And so the idea here, so normally this happens in the mesosphere stratosphere. The top stratosphere. This reaction usually happens in the lower stratosphere, where the lower intensity light penetrates. So the question is, how can the fact that if there's not a lot of ozone, how can that kind of regulate and self-heal? How can we form more ozone by the fact that there is less ozone? How does more ozone get formed faster? And it all comes down to these 2 reactions. The idea here is that if there is less ozone, more high-intensity light will penetrate further. If more high-intensity light penetrates further, then this will shift down to the lower stratosphere. More light will get to the lower stratosphere, and more of this will get zapped apart. So if there is, and will increase, it will increase the monooxygen. If there is more monooxygen, if that goes up, then the already abundant oxygen that will be there in the lower stratosphere in higher concentrations, that means this reaction will speed up. We will form more ozone because there's less ozone and more oxygen. This reaction will speed up, and so we'll replace some of the O and turn it into the ozone. And so in this way, we are going to self-heal. We're going to self-heal through that reaction. So thus reforming it. Now, problem 5. Problem 5. So a catalyst may be defined as a substance that enhances the rate of a chemical reaction without being consumed in the process. By definition, a catalyst would have an infinite lifetime. But the ozone decomposition catalysts have a finite lifetime. So what possible sinks for removal of stratospheric NO and Cl? And so the hint I give us is we only want to consider the reactions of NO and Cl and not reactions of the intermediates. So how can we remove the NO and the Cl? And it's literally just the sinks. They're like for what things will react with NO to consume it. So in the case of NO, we can have HO2 reacting with it. The hydroperoxy, we can have NO2 reacting with this. We can form nitric acid, and we can form N2O5. And so, as well as HNO2. These are places we can store these NO. OH radicals can react, as well as peroxy radicals can react with these guys. And so that those can consume and absorb my NO. Consume and absorb my NO. And so some of these are things that get formed. OH, peroxy are going to be helping form. These get moved out in these forms usually. Consumed and turned into acid rain and rained out, typically. So because there's these competing processes that can consume this, we can convert these into something else. Now, as far as Cl radical, the reactive molecules are largely methane and proton radicals can react with these guys, as well as NO2s. NO2, so we can form such things as ClONO2, get rained out. We can form and oxidize HOCl, so you can probably have some OH radicals as well. You can form HCl, and you can even form some Cl2. A lot of these can be rained out. That because we have these things that are going to convert this into something that can coagulate and absorb into the precipitation, we can remove them from the atmosphere, and so they won't infinitely catalyze the cycle. So that was problem 5. It wasn't much of something, but it's on where you look at what reactions can consume these guys. That in mind, moving straight on to problem 11. 11 says, the following proposal to repair the ozone layer has been made. The suggestion to inject negative charges into the lower stratosphere, and these would react with CFCs to produce harmless products. From your knowledge of basic chem, chemistry indicate if this process would be theoretically possible and discuss the practical requirements of it. So the idea here is that we're turning Cl radicals into charged chlorides. Charged chlorides. So if I take Cl radical is reactive. Cl minus is essentially the counter ion of a salt. And so we could do it. We could do this. We could form Cl radicals. We could possibly form OH radicals, even ClO anions. That could work. But you would need, for one thing, you need salt to precipitate. Salt to precipitate this out. And you might need some oxidative metals or something to help give the charge. But the basically thing is the main problem with this is the difficulty of getting the charges to where the CFCs and the chlorine radicals are. That there are very low concentrations of CFCs. They're very dispersed, and so it's really hard to get the charges to where they need. So it's not going to necessarily be super easy to put a charge. I mean, yes, we can maybe do some in the Arctic Circle, but even so, the area is like all the way from the most of Antarctica to like some of the lower South America. Because the low concentration would have to spread this far and wide to try to get this to mix in, and hopefully those charges won't react with other things in the meantime, and so this is going to be hard to spread the charges. So, I mean, theoretically it's possible, but ease of use, no, not really. Not really. We're almost done. I mean, we got 15, and that's really the last one. 15. What is the main natural and 15 and 16? What is the main natural and anthropogenic sources of HOX, NOx, and ClOx radical species? And then describe any connections between the natural and anthropogenic sources, the various species. So you're just looking at those. How does HOX get formed? HOX can be formed from water and methane. Those are the main sources. Now, water or the methane could be from cows and processing of the methane gas, as well as smog can help do that. Incomplete combustion. That smog can also produce our HOX. So now methane can be natural byproduct of organic decomposition, but it also can be from animals. So methane is a source for both. Water can be a natural source, or it could be an anthropogenic source, depending on how it's produced. So there's some links, but I mean it's pretty much the same chemical either way. With NOx, the main natural source is N2O, which can come from the soil. But we can also have this NOx produced by lightning and forest fires. While the NOx from anthropogenic sources largely comes, we have some fertilizers and combustions in engines. Internal combustion engine. So both of these can come from combustion, and both of these can come from the soil, but the concentration of each will vary greatly. because internal combustion engines, there's a lot more of that than we have forest fires and lightning. The N2O comes from the production in the soil, reduction in the soil. A lot less of that's going to come than, say, fertilizers we're going to put in the soil. Now, for our ClOx's, those are going to come from, we can have chloroform or the chlorocarbons, which can come from oceans and vegetative decomposition and from volcanoes. Well, the main human version of this is from CFCs and haliforms. So all of these are usually organic chlorines, but in this case, this is industrial chemicals, and these are naturally produced chemicals that they don't have a neat relationship other than the fact that they all contain some carbons in there, carbon and hydrogens in there. So that one is really kind of a short problem, just kind of like going back over and like reviewing our what produces what. The last problem real quick is although the name of a null or do-nothing cycle related to ozone depletion sounds that is effectively harmless, describe the potentially harmful effects that are associated with these types of cycles. So basically describe why this is not, the null cycle is not necessarily helpful and why it can be potentially harmful. And the basic idea here is that those null cycles, like for example forming N2O5, it stores the nitrogen. It doesn't get rid of it, it just stores it for later. So it doesn't necessarily help the environment, and it could potentially harm the environment later. In that, now this N2O5 can then travel far from the source. So now the problem becomes future problem, possibly somewhere where it can't necessarily deal with it as easily, or spreading the problem out. It does not remove the species. So this is like, for example, it travels to the Antarctica, where we have our ozone hole. So the idea is that even though it stores it and says, okay, I'm going to stop making this nitrogen monoxide or whatever right over the city where they produce the NOx, and so it stops forming smog and it stops eating away the ozone up in there, it allows this to move somewhere else by the thermal convection of the winds. So it doesn't remove it necessarily, and it just stores it for later. It's like saying, I'm going to take out a student loan, and then I'm going to defer those loans for later. The loans are still there. They're still acquiring interest. It's just I don't have to pay it right now. Well, that interest just means there's more interest to pay, and that unless I start paying on it, it's still going to keep building up, and it's just maybe going to follow me to somewhere else where maybe I'm less capable of paying for it. So in this case, it's storing it for later without removing it, and it can travel to somewhere where it's maybe a bigger problem. If it all builds up in Antarctica, suddenly we have a big problem as opposed to a spread out problem. Instead of everyone's problem, it's just one person's problem. In this case, that person is Antarctica, a continent. As I said, this is a shorter chapter, a lot less math, but it wants you to kind of think on these issues and not just simply crunch numbers. So with that in mind, I leave you with that. Have a good day.